Okay, welcome to linear algebra class. In today's class, I'm gonna do some interesting exercises. So first, we are going to finish the Markov chain, and then we are going to look at reinforcement learning. We have 4 classes. So what I'm gonna do is I'm gonna talk about in each class different types of deep learning architectures and their applications using MATLAB. So in today's class, I would talk about Markov chains. And after we finish talking about Markov chains, I'm going to talk about reinforcement learning. Anyone taking reinforcement learning class? Excellent. Okay, so probably you already know a lot about reinforcement learning. But what I'm going to do is I'm going to talk about reinforcement learning based on the controls and dynamics approach. Yes, so if you haven't taken reinforcement learning, that's a very good class to take. Now, let's continue the discussion that we started last class. In last class, we were talking about the probability and its applications. By the way, whether you believe it or not, we have finished most of the textbook. And in one of these classes, I would kind of go through the textbook and explain you what we have discussed. The only part is the textbook is fairly theoretical, and we looked at the same concept from application point of view. Especially we used MATLAB in all the applications. So in last class, we talked about Kalman filtering. So in the last class, we talked about Kalman filtering. Now in today's class, I want to talk about something called as Markov chain. Markov chain. And I would explain this Markov chain, the concept of Markov chain, by means of an example. So imagine we are going to look at 2 cities. One is Chicago. So this is Chicago. And the other city is Denver. And imagine you own a rental car business. And what you want to do is you want to find out that how these cars get distributed from Chicago to Denver. So for an example, you have 2 destinations. So you have a shop in Chicago and you have one in Denver. So this is your rental car business. So rental car. So this is car. So location A and location B. So based on the past data, so you started this business based on the past data, you found out that the 80% of the cars, 80% of the cars from Chicago stay in Chicago. So you say that 80% of the cars that are rented from Chicago, they stay in Chicago. 20% of the cars from Chicago land up in Denver. So 20% of the cars rented from Chicago land up in Denver. Now what you see here is 70% of the cars from Denver, or 0.7% or 0.7 or 70% of the cars, Denver cars, stay in Denver. 30% of Denver cars go to Chicago. So now, so if you have a car that is starting from Chicago, there is 80% possibility that the same car would stay in Chicago, that would be rented locally, or there is a 20% uh, possibility that that car would land up in Denver. So how would you write this as a classic linear algebra problem? And please understand, Markov chains is the concept, is a fundamental concept where probability and linear algebra, they come together. So as soon as you mix probability and linear algebra, Markov chain is the perfect example to start that journey. So what I'm going to do is, I'm going to write this as something like this: cars in Chicago, cars in Denver, and I'm going to write down this probability matrix. And I would say 0.8, 0.2, 0.3, 0.7. And this are the cars in Chicago and cars in Denver. So what this means is, these are the cars on an instance before, and after some time or next instance, this becomes the car composition. So think about it like this: if I say every month, so let me pose this problem. Every month, 80% of the cars in Chicago stay in Chicago, 20% of the cars in Chicago go to Denver. Same month, 70% of the cars in Denver go to Denver or stay in Denver. 30% of the cars in Denver go to Chicago. So I can come up with this type of transition probability matrix. So which means, say this was the car composition in January. And if I want to find out what would be the car composition in February, what I will have to do is, I will have to multiply that by this probability matrix. Now, if I want to project this in advance, say I want to go from January to February to March to April, all that way, then please understand, what I will have to do is, I will have to continuously multiply by this probability matrix. So this is the initial distribution of cars. So initially I had 100 cars in Chicago, 0 cars in Denver. So once I propagate this matrix, so once I say 0.8, 0.3, 0.2, 0.7, and I multiply this by the same matrix, multiply this by the same matrix. So this is going to tell me after 3 months, how many cars will be in Chicago and how many cars will be in Denver. Everyone understood this? So this is nothing but a classic Markov chain problem. Now what this Markov chain problem means? Markov chain is the chain with probabilities. So 0.8, 0.2, 0.3, 0.7, if you are to add the columns, they are going to be 1, which means the total probability is going to 1. Car can neither be created nor be destroyed. Cars won't be stolen. The cars would remain the same. Only thing is, the distribution is going to change as time goes on. So this is a classic Markov chain problem. Now, if you think about it, you can actually propagate this all the way in the future to find the steady state. So if you continue to do this process, if you multiply p by p by p by p by p by p by p by, and if you were to continue multiplying, you will realize after some times the number is not going to change. That is nothing but the steady state distribution, which means I want you to try this. I want you to start with any distribution, say 100 and 0, and multiply p, say 10 times. you will realize at the end, your number is going to be 60 and 40. You will notice that 60% of the cars would remain in Chicago. Out of 100 cars, 60 cars would go back to Chicago, 40 cars would go to Denver. Now, here is the other interesting approach. If you start with the opposite way, so you say Chicago does not have any cars, 0 cars in Chicago, 100 cars in Denver, and if you were to perform the same multiplication, you would still realize that 60% or 60 cars would land up in Chicago and 40 cars would land up in Denver. So if you have a Markov chain, the idea of Markov chain is the next outcome is dependent on the current state. The next outcome is dependent on current state. And you will realize that if you have a Markov chain, your probabilities will equate to 1. And if you were to find out the eigenvalues of this matrix P, so if you were to find out the eigenvalues of matrix P, you will notice one eigenvalue is going to be 1. And the other eigenvalue in this case is going to be 0.5. And if you find the eigenvector corresponding to the maximum eigenvalue, that is 0.6 and 0.4, that gives you the distribution of the final outcome. Now, I want you to think about what is happening here. So imagine if you have a huge Markov matrix, say, and then if you were to find out the eigenvalues and eigenvectors of that Markov matrix, it will always have 1 as its eigenvalue. And the eigenvector corresponding to that unity eigenvalue will give you the steady state distribution. So with this, you can predict what would be the distribution of car maybe after 10 months or 15 months and so on. Now there are 2 cases of Markov matrices. You can have a Markov matrix which is distributed or which is actually causing distribution. You can have another Markov matrix which can actually flip, which can actually do the flipping. So what happens in the case of flipping is you can have a Markov matrix, something like this. So I want to show you. So C, and this is Denver. This is C, this is Denver. So if you look at the way we wrote the earlier Markov matrix or Markov chain matrix, this is Chicago, Denver. You have Chicago, Denver. So this is Chicago, Chicago. This is Denver, Denver. This is Chicago to Denver. And this is Denver to Chicago. So now what I want to do is all the entities in the matrix that I have shown in the top, they are all positive. Now let me write down this something like this. 1, 1, 0, 0. If I were to write the matrix, transition matrix, something like this, what that means is all the cars in Chicago land up in Denver. All the cars in Denver go to Chicago. So can you see that the second Markov matrix and the first Markov matrix, they are different. So in second Markov matrix, you do not have the diagonal elements. The diagonal elements are 0. Off diagonal elements are 1. So in this case, basically it's flipping. So you can have 2 types of transitions. You can have a distribution or you can have the flipping. And when you have flipping, the eigenvalues are 1 and eigenvalues lambda is equal to -1. Now, what is the advantage or disadvantage of this type of analysis? So please understand, Markov matrix or a Markov chain there is something called as Markov chain, which is gives you the probabilities of transition. So you can have a hidden Markov model wherein you don't have direct access to the state, but you are observing something that gives you information about the state. And you can have various different configurations of Markov chain, and then you can actually use those to solve. Yes, here it actually transitions the exchanges. So you can actually solve different computational problems and try to predict what is going to happen in future based on the transition probabilities and based on the Markov chain. But here are some important observations about the Markov chain. So transition probabilities or probabilities, PIs, do not depend upon n, which is the iteration. The probabilities of state yn plus 1 for new state depends only on current state. And the way you do this in Markov chain is something like this. So let me give you an example. You have a current state, you have the future state, and you have something called as the transition probabilities, and you have the probabilities that are something like this. So here, this is Chicago, this is Denver. Chicago cars remaining in Chicago is 0.8. Chicago cars going to Denver is 0.2. Denver cars remaining in Denver is 0.7. And Denver cars going to Chicago is 0.3. So you will notice something like this type of a diagram. This talks about the simple state transition, and this is just a two-state transition. You can have multiple states. So for an example, you can have Chicago, Denver, and Phoenix, or you can have Washington, you can have New York. So basically what you would do is you'll form this huge Markov matrix, and these probabilities are estimated based on the data that you have. And then what you can do is, using the tools like Bayes theorem and other statistical tools, you can actually find out what would be a particular distribution at particular time, how the cars will be distributed, or how would the future look like. Now, I want to tell you a practical application of this Markov chain. Imagine you are constructing a sentence. So for an example, you use the word I, and then the next one is I am, or I want, or I do. And then what you have is, now I want you to think about these as the Markov states. And now what you have is, you have certain probabilities. And then what you have is, you have the probabilities that is relating in between. So when you are using the autocorrect based on the probabilities that is calculated, it potentially gives you the path. So, and it starts suggesting the next word in the sequence. And that is how, at a very basic level, the autocorrect or auto completion or auto sentence completion, or for that matter, if you go to Google, you start typing something and Google will start giving you suggestions. That is how it works. Now, when you are looking at the Markov chains, something very important that you always keep in mind, that is called as Perron Frobenius theorem. So Perron Frobenius theorem, and this theorem gives you an indication. It says if Aij is an element at ith row and jth column, is greater than 0, then the largest eigenvalue and also the eigenvectors are positive, then the matrix A, and Aij is an element of of matrix A, is positive. So Perron-Frobenius theorem actually can be used to analyze the Markov matrices and Markov chains. And basically that says, how do you decide if the matrix A is positive? And for that, what you need to do is you need to find out all the elements of that matrix. If they are positive, then the eigenvalue is the largest eigenvalue, and the eigenvector corresponding to the largest eigenvalue, both of them are positive. There are different types of Markov chains. There is something called as the finite Markov chain. Finite Markov chain. So in finite Markov chain, what you have is the states. You have 1, 2, 3, all the way to n. So if you have the states x1, x2, x3, and the last state is xn, that Markov chain is a finite Markov chain. You can have an infinite Markov chain. And have an infinite Markov chain. And in infinite Markov chain, you have 1, 2, 3, and this goes all the way to infinity. So you can have infinite states, and you can have a continuous Markov chain where your xn is actually a continuous vector. So basically, it's actually a continuous, not a vector, continuous function. So you can have a finite Markov chain, you can have infinite Markov chain, or you can have a continuous Markov chain. But mostly for practical applications, we are going to look at the finite Markov chains. And believe me, these Markov chains and the probabilistic nature of Markov chain is very, very applicable when we are trying to solve the problems in machine learning or data science that have probabilistic concept to it. And again, with this brief introduction on the Markov chains and the concept of probability, what I want to do is, I want to, in the next few classes, we have, I think, 4 classes. I'm going to take examples of different machine learning architectures, and then I'm going to walk you through the examples with MATLAB on what those different architectures are, what are their applications, and I will try to give you sort of a basic understanding of different concepts, different applications of the deep learning and machine learning techniques. So first, in today's class, what I'm going to do is I'm going to introduce you to something called as the reinforcement learning. And then what I would do is I would use the concepts that we talked about in probability, deep learning, and machine learning to solve problems using MATLAB in reinforcement learning. So now before I transition to reinforcement learning, any questions on the material that we have discussed so far? No questions? Okay. So let me start with the what? Yeah, well, yes.
So the condition for Aij should be greater than 0. Is that like every element?
Every element.
And when Aij, all the Ai and J are greater than 0, that means that what does that mean? It means the eigenvalues and eigenvector will be greater than 0. That's it.
No. What that means is largest eigenvalues and eigenvector are positive. And why this is important? Because if you look at the Markov matrix, that what we have here, we have all the positive numbers. So 0.8, 0.2, 0.7, 0.3. So if you find the eigenvalues and eigenvector of that, you will see you would get plus 1 as one eigenvalue, and you will have 0.6 and 0.4 as the eigenvector corresponding to 1. So what made us, so basically what is the mathematical justification for that? The mathematical justification for that comes from the Perron-Frobenius theorem, because Perron-Frobenius theorem states that if all the elements of that matrix are positive, then the largest eigenvalue and largest eigenvectors are positive.
Sorry, I don't completely follow what it means by 0.6 and 0.4.
Okay. All right. I will go ahead and let's say, can you do in MATLAB? You can do EIG 0.8, 0.3, 0.2, 0.7. You will notice you are gonna get 1 and 1/2 as eigenvalues, and what you will see is the eigenvector corresponding to 0, the eigenvector corresponding to 1 will have 0.6 and 0.4, and eigenvector corresponding to 1/2 is going to be 1 and -1. Can you check for me?
It gives 1 and 0.5.
0.8, did I do it right? 0.8, 0.3, 0.2, 0.7?
Yes, it just gave 1 and half.
1 and 0.5, right?
That's it.
Right, but then, okay, so do it like this. M n is equal to EIG 0.2, 0.7. So now it will give you eigenvalues and eigenvectors.
Is 0.8321 and percentage is minus root 2, 0.707. Sorry, 1 by root.
1 by root 2.
0.5547 and again plus 0.707. That's the number.
Okay.
Should I say it again?
So did you get eigenvalues at 1 and -1.5?
Yes.
Okay.
N is 1 and half minus n is 1.5. That's
Right. And what is M?
0.8321. 1 that's the first.
Yeah.
Element. 1 2 is minus 1 by root 2. 2 1 is 0.5547. and 2 is plus 1 by V2.
Okay. So the issue with
That's it.
okay, yeah,
Transpose is done.
okay. No, that's fine. So basically, as you can see, and you are getting 0.5 and you are getting 1. Is that right? As eigenvectors, eigenvalues.
1 and 0.5 the other way around. but
Yeah, they are.
Just switch.
Even that vector is but you have written it as a transpose. So
Okay. So what I'm trying to say here is, this is what I'm trying to say. You will get one positive eigenvalue and the eigenvectors corresponding to that positive eigenvalues will be positive. Is that what you're getting or no?
I have one negative value.
No. And second eigenvalue is different. It won't be 1. It will be different. And you can get positive or negative eigenvectors corresponding to that second eigenvalue. Does it make sense? And I want you to try this. But the idea here is, why is this happening? This happens because of this famous Perron-Frobenius theorem. Because it's saying that if all the elements of your matrix are positive, then you are going to have the largest eigenvalue and largest eigenvector are going to be positive. It doesn't matter. The other eigenvalue and eigenvector could be positive, negative, or it could be that doesn't matter. But the largest eigenvalue and eigenvector are going to be positive. And in a Markov chain, that dictates the steady state distribution of the states. That is the point. Okay, can we change P? No, P is some sort of transition. Say for an example, if your robot is standing, then that robot, if your robot is at position A, what is the probability that that robot will go to position B, or what is the probability that the robot will go to position C? What is the probability that the robot will stay at position A? So that is what is meant by the Markov matrix or the probability matrix. Yes.
So if you consider the traveling salesman problem,
Yeah.
so in the graph, we usually have the weights or the distances.
Right.
So if you replace those distances with the probability, it becomes Markov chain.
No, but then you have to write that as a matrix. But yes, you can actually. So for an example, what is the probability that the traveling salesman would go from state A to state B, or state B to state C to state D? Now, actually, the reason I wanted to talk about this a little bit, because we use this for a very practical problem. The problem that we are trying to solve was the intent prediction. Say for example, if someone is standing, okay, and wearing a robot, a wearable robot, you want that robot to respond to that person very quickly. So the idea is, what is the probability that the person who is standing will start walking or continue to stand or sit down? So what we did is we provided a transition probability matrix just like that. So you say you have 3 states: stand, walk, sit. Then if the person is standing, he will continue to stand, say 0.75% of the time, of 75% of the time. He will continue to walk maybe 20% of the times, and he will continue and he will sit 5% of the times. So basically what you do is you construct this probability matrix, so that way the robot kind of knows, sort of knows what would be the most likely action is going to be. So what you do is, then you construct something like this, and then you have to solve or call something called as the Bellman equation. And once you solve the Bellman equation, you can actually predict what would be the next possible state that is going to be. So Markov chain has lot of applications, and we'll see some of those applications in the reinforcement learning and the different the machine learning architectures that we are going to look at. So next few classes, I will talk about different applications and I will walk you through different exercises. Any other question from online students? Any questions, my online students? Okay. Now, what I'm going to do is, I'm going to start talking about reinforcement learning. But the reinforcement learning is basically, I was going to make slides, but then I found these fantastic slides. And then I thought might as well explain this with the slides that are here. So let me, in today's class, what I would do is I will discuss the theory of reinforcement learning, and if time permits, I will work out a problem in reinforcement learning, and then we will talk about some potential applications of reinforcement learning. And a quick note, I'm not going to talk about reinforcement learning from the purely machine learning aspect. My background is not in machine learning. My background is in dynamics and controls. So what I'm going to do is I'm going to try to relate the concepts in reinforcement learning to the problems in the control theory that we solve. And then actually, how do we use these fantastic reinforcement learning tool to solve practical robotics problems or practical problems. So first of all, what is reinforcement learning? So reinforcement learning is the way we learn. So for an example, that we take certain actions, every action has a consequence. We bear the consequence. So for an example, if we study, we get good grades. If we don't study, we don't get good grades. So every action has a consequence. In other words, it has a reward. It has a positive reward or it has a negative reward. So if you take the correct actions, then your reward increases. If you take incorrect actions, your reward decreases. So if you look at the reinforcement learning is sort of extension of the ideas that how we learn. So first and foremost concept in reinforcement learning is environment. So what is an agent and what is an environment? So agent is sort of a software algorithm. And when I try to talk about algorithm, please understand, this is just a mathematical description. Like if you see this, do this. That is an agent. Everything outside that agent is nothing but environment. And what is reinforcement learning? Reinforcement learning is just trying to simulate how humans learn. Many a times we don't really have a very good dynamic model, very good model of the environment. But what happens is, as we interact with the environment, based on our interaction, we learn. Say, for example, how a small baby learns to walk. He starts walking, but falls down. When he falls down, he understands that is not the thing to do. He corrects himself. And then basically that small baby starts walking. So reinforcement learning is basically how to map actions or how to look at the environment, what actions to take so that we are able to accomplish the task in hand. And one thing that is very interesting and important about reinforcement learning is reinforcement learning has been used in lots and lots of application. The example is driverless car. So reinforcement learning has been used in driverless cars. So autonomous cars. Or if you look at the Go player, AlphaGo, it is used in AlphaGo. if you look at the robots are learning robots to walk, or using robot with humans, the reinforcement learning is used in lots of applications. Now, believe me that reinforcement learning has the same architecture as a simple control scheme. So for an example, when you look at the controller, you have some sort of controller, you have some sort of environment, and you get feedback from the environment. And based on the feedback, you basically change the input. And this feedback allows you to basically change the behavior of the system. Now, reinforcement learning is exactly doing that. So basically, we are trying to control the behavior of the system, and we want to find out what actions we need so that the behavior of the system is exactly the way we want. Now, some of you might have seen adaptive control. So reinforcement learning can be thought of like a higher order adaptive control strategy. So now if you think about balancing the robot, which is shown over here, if you want that robot to balance and if you want that robot to walk, please understand there are different types of motors. Some motors controlling arm, some motors controlling torso, some motor controlling knee joint, and so on. And what you want to do is you want to make sure that all those motors, they work in sync so that robot can not only walk, but it can avoid the obstacles based on the input that the robot gets from the sensors. For an example, the robot could have vision sensor, robot could have a LiDAR sensor, robot could have maybe IMUs. So all that sensor data can be used to basically tune or in real time changing the output of the motor so that the robot can walk and avoid obstacles and also reject the disturbances. Now, what is the problem with a control system? So if you think about the control system that you need to basically make sure that the robot is able to walk, robot is able to avoid obstacles, robot is able to reject disturbances, it becomes super duper complex. It will have inner loop, it will have outer loop, it will have interconnects, and so on. And so as you can see, that problem, a simple control block problem, becomes very, very complex as you start cascading different aspects. So the hope is that this very complex control structure can be replaced by something called as a reinforcement learning. So that is the fundamental sort of building block of reinforcement learning. So if you try to design a conventional control, then you will need lot of blocks, lot of tuning. But the hope is if you were to use some sort of reinforcement learning, you will just have a function that will take some observations and that will generate actions for multiple outputs. So basically that reinforcement learning will somehow give you some actions that will adjust the torques and positions of these different motors to actually achieve the task in hand. Now, reinforcement learning is a slightly offset batch of machine learning. In the past, we studied unsupervised learning, which is sort of pattern recognition. We studied supervised learning, which is sort of labeling. And the reinforcement learning is basically learning as you interact with the external environment. And so what you have is, depending upon the actions you take, you are going to have certain type of reward. And sometimes what you do is you are going to reward in each subsequent action. And what you are going to do is you are going to actually find the value, which is not only the current reward, but potential for future reward, and based on the reward and value, you try to find out the most optimal uh, path or optimal control that can be implemented to achieve the task in hand. So we talked about unsupervised learning, which is nothing but the pattern recognition. We talked about the supervised learning, which is nothing but labeling. So where the data can be fed, and based on the features, the computer can identify, or the algorithm can identify what data that is, or what is the label of the data. Now, in the reinforcement learning, what you have is there are actually 4 basic steps. So what you have is agent interacting with the environment. So agent observes the environment, and then based on the observation, it actually takes certain type of action. Based on that action, it actually gets reward, and based on all this information, you can select the appropriate sequence of action that will maximize the reward and value. So this basically is called observation, action, reward cycle. And this cycle would continue till the whole training is completed. So this is the building block of reinforcement learning. You have agent interacting with the environment, agent observing the environment, agent doing some action, and then based on that action and observation, agent is getting some reward, and basically it actually navigates all the possible sequence of actions to maximize the reward. And this actually cycle continues till the reinforcement learning is completed. Now, here is, so in the case of reinforcement learning, what we talk about is you will encounter the words like policy. That is nothing but a simple algorithm or a mathematical function that is implemented inside the inside the reinforcement learning architecture. You will have certain inputs. So you will have certain inputs, you will have certain outputs, and then you will have a function that would actually map those inputs to outputs. So this is the basic structure of reinforcement learning. Now the idea is, if you think about the reinforcement learning, it's similar to the optimization concepts that we studied. So idea is, in the case of optimization, you are trying to minimize cost. So in the case of optimization, you are trying to minimize cost. For an example, if you are trying to find out L2 distance, then what you are trying to do is you are trying to minimize the error. In the case of reinforcement learning, you would use the same concept, but you'll maximize the reward. So in optimization, you are trying to find out minimization of cost. In the case of reinforcement learning, you are trying to maximize the reward. Now, so what does it mean? It means that we want to develop an algorithm, and that algorithm development will be done iteratively. So which means what you will do is you will run through all the possible actions, you will go through all the possible rewards, and finally you would select the sequence of actions that will maximize your reward. And that is finally going to give you this function that is actually that can be implemented in a robot or an autonomous car or the problem that you are trying to solve using reinforcement learning. So think about policy. Policy is nothing but a function, and that function is dependent on the observations or the input data, and that is going to generate certain actions. Now, please understand, the reinforcement learning is similar to traditional control. So in traditional control, what you're trying to do is you could have a PID control, you can have a nonlinear control, you can have an adaptive control. The idea is you're trying to tune the controller. sometimes the tuning is done just once. But think about reinforcement learning is that tuning is continuously done. And finally, what you do is you come up with a set of gains or you tune the controller for all possible space or all possible outcomes, all possible actions. So that is how the reinforcement learning is basically associated with traditional control. Now, this is the classic workflow. And please understand this. Anyone use MATLAB reinforcement learning toolbox? Anyone use MATLAB reinforcement learning toolbox? If you have not used, how about the students who are taking reinforcement learning? Python? Yeah, if you have not used my MATLAB toolbox, I would strongly encourage you to look at reinforcement learning MATLAB toolbox. It's fantastic. It's very visual, and you can actually look at all the, I think it has lots and lots of reinforcement learning algorithms. But I'm going to discuss this, the way the MATLAB toolbox is set up. So basically what you can do is, if you don't have any experience with reinforcement learning, you can directly go to the MATLAB toolbox and we can work out some problems. Python is fine too, but MATLAB is my tool of choice. So reinforcement learning workflow inside the MATLAB is something like you set up the environment, you set up the reward, you set up the policy, you perform the training, and then you actually deploy. So basically you go through these steps. Is the same workflow in Python too, or slightly different? Okay, all right. So you have environment, you have reward, you have policy, you train, and then you deploy. Now, what we are going to do is we are going to set up the environment. So what is environment? Environment is everything outside agent. Once again, what is agent? Agent is some sort of a function or a control algorithm or a logic that is used inside the reinforcement learning framework. Everything outside it is the environment. Now, so reinforcement learning has become very powerful because reinforcement learning can be used when there is no underlying model, which means based on the interaction with the environment, the reinforcement learning can be used to train. So you, even though you don't have an exact model, even if you have an approximate model, you can use reinforcement learning, and that can be used to solve the problems. So the next part is sometimes you can use some information that you already have available. So for an example, if you know that there is certain path that the robot should not take, or if you know that certain road the driverless car should not travel, then you can actually use that to train the reinforcement learning or the agent better. Now, there are different techniques. You can have a model-free reinforcement learning, or you can have a model-based reinforcement technique. And there are advantages and disadvantages to both. And depending upon the application that you are using, you can choose a model-free or model-based reinforcement learning. But nowadays, model-free reinforcement learning is becoming very popular because we are hoping that this model-free reinforcement learning will help us solve the problem where we don't have the perfect understanding of what's going on. Now, many a times the reinforcement learning can be trained in a simulated environment or in the real environment. Obviously, simulated environment is much better because it's cheaper, and even though you make some mistakes or if the learning fails, no big thing. But many a times after the simulation, you want to test it in the real environment. Now, you can actually, I don't know if you have looked at the MATLAB example of reinforcement learning, but this is the inverted pendulum. This is a very classic control problem. And when you go to any control class, even linear state space system, non-linear systems, adaptive control, most likely the problem they would solve is something like inverted pendulum problem. The idea is you have this pendulum that is hinged onto the block, and you want to keep that pendulum upright by moving the block or applying the torque at the base. So what velocities you need to impart to the block, or how should you move the block so that the block will balance the inverted pendulum? That is a very classic problem that is solved. The other problem that is typically solved is ball and the beam problem. So you have a beam and there's a ball on the beam, and then you want to balance that ball on the beam. So we will look at this problem. MATLAB has an excellent tutorial on how to solve this inverted pendulum problem and using the reinforcement learning. So we will look at that problem. So again, advantage of simulated environment, quicker, faster. You can perform lots and lots of iterations, and once you are comfortable with your simulation results, you can put all those results onto the actual robot. Now, I mean, I think we should be able to get to this problem. There's a very nice problem inside MATLAB, wherein you have the robot walking problem. So how do you train robot that's trying to walk using the reinforcement learning? If you have not done it, I would encourage you to take a look at it, or we will actually work out this problem in class, wherein what you have is you have a robot, and what you do is you use this reinforcement learning architecture so that after the learning is done, you would observe that this robot, it starts walking very nicely. Have you done walking robot problem in reinforcement learning class? Okay. So this is a very practical application. As a matter of fact, I have a couple of PhD students who are taking reinforcement learning class, and they actually did the reinforcement learning on UR5 that would allow the robot to go from point A to point B. So they did that as part of the reinforcement learning project. But I think they used Python. You can do something similar using MATLAB. So something interesting. If you guys really want, and if you are building that robot arm, maybe you can use reinforcement learning so that the robot goes smoothly from point A to point B. That is certainly possible. So, okay, now the next we looked at the first part of reinforcement learning. Now, what we want to do is we want to just sort of look at what is this reward and what is the policy structure. And please understand, depending upon how you look at it, or depending upon whether you follow computer science, whether you follow mechanical engineers or applied engineers, everyone looks at rewards and policy structures slightly differently. But if you think about the reward, it's basically think about the carrot dangling in front of a donkey. So basically, reward is what you get if you perform the action. And reward, very simply, can be stated as this is a mathematical function. And please note, this is just a scalar number, okay? This is just a number. So if you enter, or if you provide certain state, if you provide certain action, that function will take that state and action information and give you a number. That is basically the reward. Now, this reward is closely related if you have taken the LQR control, linear quadratic control, or Gaussian control, or stochastic control. You will see that this reward type of function is similar to the cost function in the LQR control, where what you have is you have certain performance and you have certain effort. And what you want to do is you want to maximize the performance but minimize the effort. So and you want to find out a cost function or a control policy that maximizes the performance but minimizes the effort. So the reward in reinforcement learning is something similar to the cost function that you see in optimal control. So many a times what you want is, you don't want the rewards could be sparse. For an example, if you want robot to go from point A to point B, you want to reward when the robot reaches point B, not when the robot goes from point A to an intermediate point. So what you can have is, you can have rewards that are sparsely spaced, which means the rewards, they are not distributed, they are discrete, and the actions get rewarded after satisfactory outcome of meeting certain goal. So you can have sparse rewards. So for an example, if you want robot to go from point A to point B is at 10 meters, your reward is going to become 1 when the robot reaches 10 meters, and the reward will be 0 if the robot has reached anywhere less than 10 meters. And many a times what you want to do is, it's very difficult to have the reward at the end. So and just to continue so I'll give you a very simple example. So for an example, if someone tells me, you work for me for 1 year and I would give you $1 million, that will not be as attractive as, you work for me and every month I will give you $100,000. So that is the difference between the reward shaping. So rather than a big reward at the end, you can have rewards at intermediate steps. That is nothing but something called as the reward shaping. So if you want robot to walk 10 meters, rather than giving, say, 1 unit a reward at the 10 meters mark, you just give 0.1, 0.1, 0.1 in 10 increments. But the problem there is, you will notice that the robot, what you want is, you want robot to be upright and walk. But if you actually shape the reward in such a way, the robot, what will do is, it will try to go from point A to point B, not by walking, but maybe crawling, maybe falling, somehow traveling that distance, but not walking. So that is the disadvantage of reward shaping. So what you do is, you can add something called as the domain specific knowledge. So what you want is, you come up with a function where you add additional conditions that, hey, the robot needs to be straight, robot needs to be walking straight, the trunk should be upright, and he should move left and right arm, he should not fall down, and minimize actuator efforts, and so on. And then basically come up with a function that is dependent on the domain specific knowledge. So what you know about the problem. Now there are two concepts to it. There is one exploration and there is exploitation. In exploration, in the reinforcement learning, exploration means actually investigating all possible space. But the problem with exploration is that it's going to take lot of time. And exploitation is basically, what you do is choosing the action based on the past knowledge, or exploiting the knowledge that the robot or the agent has. Now, there are issues with pure exploitation. There are issues with pure exploration. The idea is, basically what you do is, you balance exploitation and exploration. And as you can see that, once again, a bird in hand is better than 2 birds in a bush. So basically what you do is, you basically optimize exploitation and exploration so that your value is increased. So again, there are issues with pure exploration. There are issues with pure exploitation. What you want to do is, you want to balance exploration and exploitation so that the optimal policy is learned within the, yeah. So we'll talk about actor and critic in just a minute. So we are not there yet, but we'll get there in few minutes. So basically that is the balance that you want to obtain. Next problem is value. So please understand, this is an important concept. Reward is nothing but the instantaneous benefit. Value is nothing but the cumulative benefit or cumulative expected benefit. Now, why value is important? The value is important, which means even though your reward in short term is less, if you were to continue the path, the total reward in long run will exceed the total, it will be the best or the most optimal or the best possible reward. That's why what you have is you have concept of value. So reward is the instantaneous benefit and value is the anticipated cumulative benefit. And now here is a very simple example. You have different state S1, S2 and S0. So robot wants to decide whether robot wants to go left or right. Now, based on the reward structure, obviously the robot would want to go left because on the right, the reward is -1. But please understand, if the robot goes towards right from state S2 to state S4, all of a sudden the reward goes to +5. But unless we find the value, like, hey, what is the total value if you go to state 4 rather than going to state 1, we will not know what is the best possible action to take. So that's why you have something called as the reward and you have something called as a value. Value is the cumulative expected benefit and reward is the immediate benefit that you get. And again, what you want to do is many a times in reinforcement learning, just like in financial markets, it's better to be short-sighted, which means it's better to book the profit now than to wait for a larger profit at the end. So what you do is, and the reason for that is many a times you do not know the future because it's more probabilistic. So that's why what we do is we have the discount factor. The discount factor allows us to take into account the, so basically it penalizes the reward in future. So basically the discount factor is also used in reinforcement learning. And what is policy? Policy is nothing but the function. And if you think about it, the agent, if you look at the agent has policy and the reinforcement learning algorithm. And basically the agent does interact with the environment. It actually gets some observation, it performs some action, and it gets some reward. That reward is fed into the reinforcement learning algorithm that is actually tuned. That update is fed to the mathematical function or the algorithm in the policy, and then you update that into an action. So now policy is nothing but a function of observations, and there are direct policies and indirect policies. So what I'm going to do is I'm going to stop here and I would discuss the theory part of the reinforcement learning on Q learning or deep Q learning and all that in next class. And then what I would do is I would actually talk about actor critic, and then we will work out some practical examples using MATLAB on the reinforcement learning. So I'm going to stop here and I would be happy to answer any questions you may have.